Good morning, everyone, and welcome. I'm Dr. Sandip Parekh, a physical therapist with a PhD and a master in physical therapy specializing in musculoskeletal and sports conditions. Today, I'm excited to introduce you to the fundamentals of high-frequency currents. In this presentation, we'll explore the basic principles, applications, and benefits of high-frequency currents in physical therapy. Let's get started and dive into this fascinating topic together. Magnetism is a fascinating natural phenomenon that plays a crucial role in many aspects of our daily lives. On this slide, I want to highlight some key points about magnetism and how it connects to the broader theme of physical forces and their applications. First, magnetism is a force that arises from moving electric charges, which means it's deeply connected to electricity itself. This is why electric currents produce magnetic fields and vice versa. It's also important to understand that magnets have two poles, north and south, and these poles create magnetic fields that influence other magnetic materials or charges nearby. The most familiar example is a simple bar magnet, but magnetism is everywhere, from the Earth's magnetic field that guides navigation to the magnetic storage in our computers and smartphones. Recognizing these connections helps us appreciate how fundamental magnetism is to technology and natural processes. So, as we move through this presentation, keep in mind how magnetism underpins many innovations and phenomena that shape our world. A magnet is an object which exhibits certain properties. For example, when free to rotate, it will align itself in the north-south direction. It also has the power to attract and produce magnetism in certain other materials. So, a piece of substance which possesses the property of attracting small pieces of iron towards it is called a magnet. When we talk about magnets created through artificial means, we refer to them as artificial magnets. These are made by taking a piece of substance and inducing magnetism in it, often by rubbing it with a magnet. This process allows us to produce a magnetic field in a material that wouldn't naturally have one. It's important to understand that if the property of magnetism occurs naturally in a substance, then we call that a natural magnet. So, in essence, artificial magnets are man-made, while natural magnets are naturally occurring. Both play a crucial role in understanding how magnetism works and how we can utilize it in various applications. No matter how many times a magnet is divided, it will always present a north and a south pole. This is a fundamental property of magnets that remains true regardless of how small the pieces become. Now, this idea might seem straightforward at a macroscopic level, but it actually extends down to the molecular level. It's thought that the revolving electrons within molecules produce their own north and south poles, essentially creating tiny magnetic fields. These are what we call molecular magnets. This concept is a key part of the molecular theory of magnetism, which helps us understand how magnetic properties originate at the smallest scales. It connects beautifully to the overall theme of how magnetism is a fundamental and pervasive force, influencing both large objects and individual molecules alike. So, in a non-magnetized state, these molecular magnets are arranged in a haphazard way, meaning their magnetic effects cancel each other out. It's kind of like a bunch of tiny magnets pointing in random directions, so overall, there's no magnetic field. But when we magnetize the material, something interesting happens. The molecular magnets become ordered, aligning themselves so that one end of the piece of metal exhibits a north pole and the other end a south pole. This orderly arrangement is what creates a noticeable magnetic field. This concept is central to understanding how magnetism works at the molecular level, and it helps explain why some materials are magnetic while others are. Let's talk about what we mean by a haphazard arrangement. Essentially, this refers to a setup or organization that lacks a clear structure or systematic planning. When things are arranged in a haphazard way, they might seem random or chaotic, which can lead to inefficiencies or confusion. This kind of arrangement often occurs when there's no deliberate strategy behind placement or order, making it difficult to predict outcomes or streamline processes. It's important to recognize this because, in many cases, a haphazard setup can hinder productivity and create obstacles that could otherwise be easily avoided with better planning. Throughout our overall discussion, keep in mind how important it is to move away from such disorganized approaches towards more deliberate, thoughtful arrangements. This shift can significantly enhance efficiency, clarity, and ultimately, success in our projects or operations. So on this slide, we're focusing on the concept of ordered arrangement. Essentially, this means that the way we organize or structure elements is crucial. When we talk about an ordered arrangement, we're emphasizing that the sequence or positioning matters significantly. It's not just about having a collection of items, but about how those items are arranged in a specific, intentional way. This idea connects directly to our overall theme of efficiency and optimization, because a well-ordered setup can streamline processes and improve outcomes. Recognizing the importance of order helps us understand how to better plan and execute tasks systematically, ensuring everything aligns toward our goals. Magnetization by contact is a fascinating process that highlights how magnetic properties can be transferred directly through physical contact. When two magnetic materials touch, the magnetic domains in one can influence those in the other, effectively magnetizing the second material. This method is particularly useful for creating magnetic connections without the need for external magnetic fields. It's a practical way to induce magnetization in a controlled manner, especially in manufacturing or repair processes. Understanding this contact-based magnetization helps us see how magnetic properties can be manipulated locally, which ties into the overall theme of how we can control and utilize magnetism in various applications. Let's take a closer look at the magnetic field. The magnetic field is an invisible force field created around a magnetic object or a current-carrying wire. It's what causes magnetic forces to act at a distance, influencing other magnetic materials or moving charges. Think of it as the area where magnetic influence exists. It's essential for understanding how magnets interact with each other and with electric currents. The strength and direction of this field are represented by magnetic field lines, which help us visualize the magnetic influence in space. Recognizing the properties of magnetic fields is key to understanding many phenomena in electromagnetism and their applications in technology. Now let's talk about the points inside a magnet where attraction is maximum. These are called poles. Every magnet has two poles, a north pole and a south pole. If you suspend a magnet freely, it will naturally align itself in the direction of geographic north and south. The end of the magnet that points towards the north is called the north-seeking pole, or simply the north pole. Similarly, the end that points towards the south is called the south-seeking pole, or the south pole. These poles are crucial because they determine how a magnet interacts with other magnetic objects. Understanding the concept of poles helps us grasp how magnets attract and repel each other, which is fundamental to the overall study of magnetism. As we look at the setting in a north-south direction, it's important to understand that the Earth itself functions like a giant magnet. This means that the Earth's magnetic field will influence a suspended magnet, causing one of its poles to settle in the direction of the Earth's north pole. Essentially, if you hang a magnet freely, you'll see it align itself with the Earth's magnetic field, pointing toward the north. Now let's talk about magnetic poles. Like poles, north to north and south to south actually repel each other. So if you bring two north poles close together, they'll push away from each other. The same goes for south poles, they repel one another as well. In contrast, unlike poles, north and south attract each other. This attraction is what makes magnets stick together when opposite poles are facing each other. This fundamental property of attraction and repulsion is key to understanding how magnets work. So, in summary, a magnet's behavior is governed by these properties of magnetic poles and their interactions with Earth's magnetic field. Recognizing this helps us see how magnetic forces operate in the natural world and in various applications, connecting to the broader theme of understanding magnetic phenomena. Let's talk about how properties are transmitted in magnets. A magnet can actually induce magnetic properties in suitable materials. For example, When you stroke one pole of a bar magnet along a piece of iron or another magnetic material, something interesting happens. The opposite poles of the molecular magnets inside that material are attracted towards the magnet. This causes the entire object to become magnetized. Now, this attraction isn't just random. It's a specific effect called magnetic induction. Magnets tend to attract certain materials, like iron, nickel, and cobalt. This attraction is a direct result of the magnetic field influencing those materials, turning them temporarily or permanently magnetic. Understanding these properties helps us see how magnets can influence and transmit magnetic properties to other objects, which is a key part of how magnetism works overall. It's fascinating how a simple process like stroking a magnet can magnetize an entire object through this induction effect. Today, we're going to explore the fascinating concept of electromagnetism. Electromagnetism is a fundamental force that combines electricity and magnetism into a single unified theory. It explains how electric currents produce magnetic fields and how changing magnetic fields can induce electric currents. This relationship is at the core of many technologies we rely on daily, from electric motors to transformers. Understanding electromagnetism helps us see the interconnectedness of these phenomena and how they drive modern electrical and electronic systems. So, as we move through this presentation, keep in mind how these principles form the backbone of many innovations in science and engineering. Electromagnetism is one of the 4 fundamental forces that we know exists in the universe. It plays a crucial role in many of the technologies we use every day. An electromagnet is typically made up of a coil of wire wound around an iron bar. When we pass an electric current through the wire, it magnetizes the iron bar through a process called induction. This creates a magnetic field, turning the iron bar into a temporary magnet. Interestingly, as soon as we turn off the current, the magnetic effect disappears. Now, if we look at straight wires carrying electric current, they generate magnetic fields around them in the shape of concentric circles, with the wire at the center. This fundamental relationship between electricity and magnetism is the basis for many electromagnetic devices and principles that we'll explore further. Electromagnetic induction is essentially the process by which we generate electricity from magnetism. It's all about the interaction between a conductor, like a wire, and magnetic lines of force, which are the invisible magnetic fields around a magnet. What's fascinating is that this process can happen even without direct contact between the magnet and the conductor. Instead, the magnetic lines of force surrounding the magnet induce an electromotive force, or EMF, in the conductor. This principle is fundamental to how many electrical devices and power generators work, connecting the idea of magnetism directly to the generation of electrical energy. It's a powerful concept that underpins much of our modern technology, illustrating the seamless connection between magnetic fields and electricity. Now, let's take a closer look at the factors essential to electromagnetic induction. First, we have the conductor. The conductor is the material through which the electric current is induced, typically a metal like copper or aluminum. Its properties, such as conductivity and shape, play a crucial role in how effectively induction occurs. Next, we need to consider the magnetic lines of force, or magnetic flux. These lines represent the magnetic field around a magnet or a current-carrying coil. The strength and direction of this magnetic field are vital because electromagnetic induction depends on changing magnetic flux. Finally, all of this centers around electromagnetic induction itself, the process by which a changing magnetic field induces an electric current in a conductor. When these factors come together, a conductor in a changing magnetic field, an electric current is generated. Understanding these key elements helps us grasp how electromagnetic induction powers many electrical devices and systems we use daily. If the conductor is part of a closed circuit, the magnetic lines of force actually produce an EMF, which is an electromotive force. This EMF causes the electrons within the conductor to start moving. To see this in action, we can connect an ammeter across a coil of wire. When we move a magnet into or out of the coil, the magnetic lines of force cut across the wire. This cutting action results in a flow of electrons, creating an electric current. This phenomenon, known as electromagnetic induction, is a fundamental principle behind many electrical devices and generators. It's important because it shows how changing magnetic fields can generate electricity, linking magnetic and electrical energy in a very direct way. This principle underpins much of our modern electrical technology and helps us understand how generators produce power. Now, these electrons, as they move, repel the electrons next to them and so on, which results in a current being set up in the circuit. You can actually see this in action when the ammeter needle moves, indicating that current is flowing. But here, the key point, this movement and the resulting current are only observed when either the magnet or the coil is moving. If the magnetic lines of force stay stationary relative to the coil of wire, then no induction occurs. This principle of electromagnetic induction is fundamental because it shows us that a changing magnetic environment is necessary to generate an electric current. It ties directly into our overall theme of how electricity and magnetism are interconnected, emphasizing that motion and change are essential for inducing current in a circuit. So, what we're looking at here is how an alternating current in the primary coil can create a dynamic magnetic field. Essentially, the current causes the magnetic field to build up, then fall, and then build up again in the opposite direction. This cycle continues, creating a back-and-forth movement. The current itself has a characteristic pattern. It gradually increases to a maximum positive value, then decreases to 0. Next, it drops to a maximum negative value before returning back to 0. This constant rise and fall of the current is what makes the magnetic lines of force move. This process is fundamental to electromagnetic induction because it's the changing magnetic field that induces a voltage in the secondary coil. By alternating the current, we ensure that the magnetic flux is constantly changing, which is key to generating continuous electrical power. So, in essence, this cycle of building up and collapsing magnetic fields underpins how transformers and many other electromagnetic devices operate efficiently. It's a core principle that connects directly to the overall theme of electromagnetic induction and energy transfer. The direction in which the magnetic lines of force move relative to the conductor plays a crucial role in determining the direction of the induced current. Think of it this way. When we use a bar magnet and a coil, the movement of the magnet influences the current flow inside the coil. For example, as you move the magnet into the coil, you'll see the ammeter needle deflect in one direction. But then, when you withdraw the magnet, the needle deflects in the opposite direction. This back-and-forth movement clearly shows that the current's direction depends on whether the magnetic field is increasing or decreasing in that area. This is a key concept because it demonstrates that the induced electromotive force, or EMF, isn't just about the presence of a magnetic field, but also about how that field changes and moves relative to the conductor. The important takeaway here is that revering the movement of the magnet reverses the direction of the induced current. So, in the broader context of electromagnetic induction, understanding this relationship helps us control and predict how currents are generated in various devices and systems. The direction of the induced EMF is fundamentally linked to the motion and orientation of the magnetic field relative to the conductor. This depends upon two factors: the rate of change of the magnetic field and the inductance of the conductor. Essentially, the quicker the magnetic field changes, the greater the induced EMF will be. And at the same time, the inductance of the conductor plays a crucial role in how much voltage gets induced. The key idea here is that the strength of the induced EMF is directly related to these two factors. So, understanding how fast the magnetic field varies and the properties of the conductor helps us predict the magnitude of the induced voltage. This ties back to the overall theme of electromagnetic induction, how changing magnetic environments influence electric currents and voltages in conductors. The more rapid the movement of the permanent magnet, the more it influences the magnetic field around the conductor. Additionally, the stronger the magnet we use, the greater its magnetic force. These two factors, speed and strength, directly impact how quickly the magnetic lines of force cut through the conductor. When these lines cut through the conductor more rapidly, it induces a larger electromotive force, or EMF. This concept is crucial because it highlights how the rate of change of the magnetic field directly affects the amount of induced EMF. Essentially, faster movement and stronger magnets lead to more significant electrical induction. This is a key principle in electromagnetic induction, which underpins many electrical generators and transformers. So, in summary, the speed and strength of the magnet's movement are vital in determining how much electrical energy we can generate through changing magnetic fields. Inductance is the ability of a conductor to have a current induced in it. It's measured in henries, which is the standard unit for inductance. While the inductance of a specific conductor remains constant, you can actually design it to have a higher inductance by applying a few key principles. For example, using many turns of wire in the coil increases the inductance because more loops mean more magnetic field interaction. Placing those turns close together also helps, as it strengthens the magnetic coupling. Additionally, winding the coil onto a soft iron core significantly boosts inductance, thanks to iron's magnetic properties. These design techniques are important because they allow us to control and optimize the inductance based on the needs of the circuit or device we're working with. This ties into the overall theme of understanding how conductors and coils behave in electrical systems. Let's take a moment to focus on laws, which are a crucial part of understanding the broader context we're exploring. Laws set the formal rules that govern behavior within societies, providing structure and order. They help ensure fairness and protect individual rights, which is essential for creating a stable environment. Throughout this presentation, we've seen how laws influence various aspects of our lives, from business practices to personal conduct. It's important to recognize that laws are not static. They evolve over time to reflect societal values and needs. By understanding the key principles behind laws, we can better appreciate how they support or sometimes challenge the themes we've been discussing. Ultimately, laws are the foundation that helps us navigate complex social systems and work toward a more just and organized society. Lenz's law is a fundamental principle in electromagnetism that describes the direction of an induced current in a conductor due to a changing magnetic field. It's named after Heinrich Lenz, a German physicist who formulated this law back in 1834. So the key point here is that whenever there's a change in magnetic flux, meaning the magnetic field passing through a conductor, the induced current will always act to oppose that change. In other words, the current creates its own magnetic field that tries to cancel out or resist the original change in the magnetic field. To put it simply, if you imagine pushing a magnet towards a coil, the coil will generate a current that pushes back against the magnet's motion. This opposition is at the heart of Lenz's law and is essential for understanding how electromagnetic induction works in devices like transformers and electric generators. Overall, Lenz's law helps us understand the natural tendency of induced currents to resist the change that created them, which is a crucial concept for grasping the broader themes of electromagnetic interactions. Now let's talk about the device shown here, known as a choke coil. It is an essential component included in circuits to produce what's called a self-induced EMF. This EMF helps to maintain a smooth flow of current through the circuit, preventing sudden changes that could cause issues. Choke coils come in two main types: low-frequency choke coils and high-frequency choke coils. The difference between them primarily lies in their design and the frequencies they are optimized for. Understanding these two types is important because each is used in different applications, depending on the frequency of the signals involved. Overall, choke coils are fundamental in controlling and stabilizing current flow, making them vital in many electrical and electronic circuits. Let's take a closer look at the low-frequency choke coil. This coil typically has a wound on a laminated soft iron frame, which helps to reduce eddy currents and improve efficiency. Usually, You'll find it on the central bar of a rectangular frame, providing a sturdy support structure. The coil itself consists of many turns of insulated wire, carefully wound to create the desired inductance. The main purpose of this choke coil is to oppose changes in current, especially at low frequencies, acting as a filter or impedance element. Understanding how these coils are constructed and function is crucial in designing effective electrical circuits, particularly in applications where controlling current flow is essential. This concept ties back to our overall theme of managing electromagnetic properties in circuit design. When a current, which varies in intensity, is passed through the coil, it creates magnetic lines of force. These magnetic lines are set up around the coil and they cut through the turns of wire. As they do, they induce an electromotive force, or EMF, in the wire itself. Now, since the coil has many turns of wire, it has a significant inductance. This means that the self-induced EMF generated in the coil can be quite large, especially when the current changes rapidly. This is why choke coils, especially low-frequency chokes, are so useful. They help limit or smooth out changes in current. The large inductance effectively opposes rapid fluctuations in current, making them essential components in many electrical circuits. Connecting this to the overall theme, understanding how coils and inductance work helps us design better filters and energy storage devices. So, in essence, the more turns a coil has, the greater its inductance and its ability to resist sudden changes in current. The core's main purpose is to concentrate the magnetic field, making the magnetic flux stronger where we need it. It's typically made of soft iron, which is important because soft iron can be easily magnetized and demagnetized, allowing the magnetic field to be controlled efficiently. Also, to reduce energy losses caused by eddy currents, the core is laminated. Laminations are thin layers of iron insulated from each other, which help prevent these currents from circulating and wasting energy. Moving on, you'll notice the term low-frequency choke coil, or simply choke coil. This component is used to block or filter out high-frequency signals while allowing low-frequency currents to pass. It's a crucial part of many circuits because it helps smooth out the power supply and reduce unwanted noise. So, in the bigger picture, these components, like the core and choke coil, are essential for ensuring the proper functioning and efficiency of electrical and electronic systems. When dealing with a high-frequency current, it varies very rapidly in its intensity. This rapid variation tends to produce a considerable self-induced EMF, which can affect the circuit's performance. Because of this, we don't need to have many turns of wire in a high-frequency choke coil, unlike in low-frequency applications. In fact, winding many turns or using a soft iron core isn't necessary here. Instead, the coil usually consists of several turns of insulated wire wound on a bobbin made of a non-conducting material. This design helps manage the high-frequency currents effectively while keeping the coil compact and efficient. It's a key concept in understanding how high-frequency choke coils work within radio frequency and high-speed electronic circuits. To even out the variations in the intensity of the current, providing a smooth current flow, we rely on the self-induced EMF. When a varying current passes through a choke coil, it creates this EMF that opposes changes in the current. This means that the EMF acts to slow down the rapid rise of current to its maximum value, and it also helps to extend the duration of the current when it's falling. Essentially, it smooths out the fluctuations, maintaining a more consistent and even flow of current throughout the circuit. Now, moving on to the uses of a choke coil, it's primarily employed to control and stabilize current flow in electrical circuits. It plays a vital role in reducing noise and suppressing voltage spikes, making circuits more reliable and efficient. So, understanding how a choke coil works helps us appreciate its importance in various electrical applications, especially where steady current is crucial. To prevent the flow of a high-frequency current and allow the passage of the low-frequency one, we use a component called a choke coil. When a high-frequency current passes through a choke coil, the inductive reactance becomes quite significant. This means it resists the flow of high-frequency currents, effectively retarding or blocking them. On the other hand, low-frequency currents face less opposition and can pass through more easily. This property makes choke coils very useful in various applications, especially in filtering out unwanted high-frequency signals. They help us control and direct the flow of currents based on their frequency, which is essential in many electrical and electronic systems. So, in essence, the choke coil acts as a sort of gatekeeper, letting low frequencies through while holding back the high ones, helping us manage signals more effectively in our circuits. Now, let's talk about passing circular currents, which are often called eddy currents. You might have heard of this setup referred to as an eddy, and it's essentially a way to describe these swirling loops of current. These currents occur through conductive materials when they are exposed to changing magnetic fields. Any conductor lying in a varying magnetic field will have an electromotive force, or EMF, induced in it. This is a fundamental concept of electromagnetic induction. If the conductor is solid, the magnetic lines of force will generate these circulating currents within the material. These eddy currents are interesting because they form circular patterns, hence the name, and they can cause various effects, like heating or magnetic damping, which are important in many applications. Understanding how these currents are induced and how they behave helps us better grasp the interaction between magnetic fields and conductors, which is at the core of many electromagnetic devices and systems. Let's explore how eddy currents are generated according to Joule's law. When a changing magnetic field interacts with tissues or conductors, it induces these circulating currents. These currents are produced in lines of force and cause heating effects within the material. In the figure shown below, we have a solid conductor labeled B that is placed within a varying magnetic field. This variation in the magnetic field induces eddy currents in the conductor, which are indicated by the arrows pointing both up and down. The key point here is that eddy currents flow perpendicular to the lines of magnetic flux. This perpendicular flow is crucial because it explains how energy is transferred and why heating occurs in these conductors. Understanding this concept helps us grasp how electromagnetic fields interact with tissues or materials, which is central to many applications, from medical devices to electrical engineering. It's all about how changing magnetic fields induce circulating currents, leading to heating effects that we need to control and utilize appropriately. Let's take a closer look at the transformer model. This architecture has revolutionized how we handle natural language processing tasks. It primarily relies on a mechanism called self-attention, which allows the model to weigh the importance of different words in a sentence, regardless of their position. This is a huge leap forward from previous models that processed data sequentially. Transformers enable us to capture long-range dependencies more effectively, making them incredibly powerful for understanding context. They also facilitate parallel processing during training, which significantly speeds up the learning process. Overall, the transformer is a key component in many advanced language models today, and understanding its core ideas helps us appreciate how modern AI systems achieve such impressive understanding and generation of human language. This device is used for changing low alternating voltage at high current. It allows us to modify the voltage levels without losing energy in the process. Essentially, it helps us step up or step down voltage efficiently, which is crucial in power transmission. By doing so, we can transmit electricity over long distances with minimal losses. The key takeaway here is that this device enables voltage transformation without energy wastage, making our electrical systems more efficient and reliable. This concept ties into the overall theme of optimizing power distribution and ensuring energy conservation in our networks. Today, we're going to look at the three main types of transformers. Broadly speaking, they are static transformers, variable transformers, and autotransformers. Static transformers are the most common. They work on the principle of electromagnetic induction and are used to step voltage levels up or down without moving parts. Variable transformers, on the other hand, allow us to adjust the output voltage manually, giving more control in applications like testing or calibration. And then we have autotransformers, which are a bit different. they share some windings between the primary and secondary, making them more compact and efficient for certain voltage adjustments. Recognizing these types helps us understand how different transformers suit various electrical needs, connecting back to our overall theme of efficient power management. Now, let's talk about the static transformer. This device operates on the fundamental principles of electromagnetic induction, which means it uses magnetic fields to transfer energy. Its main purpose is to alter the voltage of an alternating current, either stepping it up or stepping it down, depending on the needs of the system. Additionally, it plays a crucial role in making the current earth-free, or in other words, ensuring safety by isolating the system from the ground. This is essential for protecting equipment and personnel. Overall, the static transformer is a key component in electrical power systems, enabling efficient voltage regulation and safety measures. This slide shows the basic construction of a static transformer. It consists of two coils of insulated wire, which are the primary and the secondary coils. These coils are wound around a laminated soft iron core. The primary coil is connected to the input voltage, and the secondary coil delivers the transformed voltage to the load. The laminated iron core is crucial because it helps channel the magnetic flux efficiently while reducing energy losses due to eddy currents. This design allows the transformer to transfer electrical energy from one circuit to another with minimal loss, which is the core principle behind how transformers work in power systems. So, understanding this construction is fundamental to grasping how transformers efficiently step up or step down voltages in real-world applications. Now, let's take a closer look at the construction of static transformers. The coils are completely insulated from each other, which is crucial for safety and proper functioning. Usually, one coil contains more turns of wire than the other, which helps in stepping voltage up or down as needed. The frame itself is often rectangular in shape, providing a sturdy structure. The coils can be wound on opposite bars of this frame, or sometimes stacked one on top of the other on a central bar. These design choices are key to ensuring the transformer works efficiently and reliably. Understanding this construction helps us appreciate how transformers are built to handle electrical energy safely and effectively. Let's break down how a static transformer works. When an alternating current flows through the primary coil, it creates a magnetic field that varies with time. This changing magnetic field then cuts through the secondary coil, which induces an electromotive force, or EMF, in it. What's important here is that there's no direct electrical connection between the primary and secondary coils. Instead, energy is transferred through this magnetic field via electromagnetic induction. This is a key concept that differentiates transformers from other electrical devices. Now, to make this process efficient, we use a core, usually made of soft iron. The role of this core is to concentrate the magnetic field, making the transfer of energy more effective. Soft iron is ideal because it can be easily magnetized and demagnetized, which is essential for the alternating magnetic fields involved in the operation. So, in essence, a static transformer relies on this interplay of alternating current, magnetic fields, and the core to transfer electrical energy from one circuit to another without direct contact. This principle is fundamental to how we manage power distribution efficiently across long distances. Let's talk about how transformers work to alter the voltage of an alternating current. The key idea here is that the electromagnetic force, or EMF, induced in the secondary coil depends on the number of turns of wire it has compared to the primary coil. This relationship is crucial because it determines whether the transformer steps up or steps down the voltage. Depending on the number of turns, we classify transformers into different types. A step-up transformer has more turns on the secondary coil than on the primary, so it increases the voltage. Conversely, a step-down transformer has fewer turns on the secondary, reducing the voltage. There's also something called an even ratio transformer, which maintains the same voltage level between primary and secondary coils. And then, we have static transformers, which are the most common type. They operate without moving parts and function purely through electromagnetic induction. All of these variations serve the overall purpose of efficiently managing voltage levels for different applications in power systems. So, understanding how the turns ratio influences the EMF helps us grasp how transformers can either boost or lower voltage as needed. Now, let's talk about what happens when the number of turns in the secondary coil is more than that in the primary. In this case, the voltage that's developed in the secondary will actually increase, or in other words, it gets stepped up. This kind of transformer is known as a step-up transformer. It's quite useful in scenarios where we need to elevate voltage levels, such as transmitting electricity over long distances efficiently. So remember, when the secondary has more turns than the primary, the transformer boosts the voltage, making it a step-up transformer, an essential component in power distribution systems. This arrangement produces a step-down transformer. In other words, it is such an arrangement where the secondary coil has fewer turns than the primary. When that happens, the EMF, or voltage, in the secondary will be less than in the primary. This is what makes it a step-down transformer, reducing voltage from one side to the other. The key point here is that by having fewer turns on the secondary, we effectively lower the voltage, which is useful in many applications where we need to reduce high voltages to safer, usable levels. This concept ties into the overall theme of how transformers can control and modify voltage levels efficiently. If the number of turns in the primary and secondary coils are the same, then the voltage in the primary is actually the same as that in the secondary. This type of device is what we call an even ratio transformer. Now, it's really important to remember that, in these transformers, the electrical power in both the primary and secondary circuits remains always equal. So, even though the voltages are the same when the turns are equal, the overall power transfer stays consistent. This concept is fundamental because it helps us understand how transformers can be used to efficiently transfer energy without changing the voltage when needed. It ties into the broader idea of how transformers can be designed for specific purposes, maintaining power while adjusting other parameters. This slide shows a basic setup of a transformer, which has a primary and a secondary coil. The interesting part here is that it's constructed in such a way that one of these coils can be adjusted in length. This adjustability is what makes it a variable transformer. By changing the length of the coil, we can alter the magnetic coupling between the coils, which in turn affects the voltage transformation ratio. This flexibility is really useful in applications where precise voltage control is needed. Overall, this design highlights how transformers can be tailored for specific voltage requirements, making them versatile components in electrical systems. Now let's take a closer look at the primary coil. It has a number of tapings taken from it, which means we can draw multiple connection points along its length. By turning a knob, we can make a movable contact touch any one of these tapings. This setup allows us to select different points on the coil, effectively changing the number of turns in the circuit. The key idea here is that when we decrease the number of turns in the primary coil relative to the secondary, it causes a step-up in voltage in the secondary coil. This means we can increase the voltage delivered to the load by adjusting the tapings, providing a very crude but useful way to control voltage. This is essentially the principle behind a variable transformer, sometimes called a variac. It offers a simple method to adjust voltage levels, which is crucial in many applications where precise voltage control is needed. Overall, this mechanism helps us understand how we can manipulate the transformer ratio to achieve desired voltage outputs, fitting into the broader theme of adjustable power control in electrical systems. This slide shows a simple coil of wire with 4 contact points coming from it. What's interesting about this setup is that it can function as a transformer, either stepping up or stepping down voltage. Now, this is what we call an autotransformer. Unlike the traditional transformer, which has separate coils for the primary and secondary, an autotransformer uses a single coil with multiple contact points. This design allows for a more compact and often more cost-effective solution. The key idea here is that by adjusting the contact points, you can control the voltage transformation. This makes autotransformers useful in various applications where voltage adjustment is needed efficiently. So, understanding this simple yet versatile device helps us see how transformers can be adapted for different practical needs in electrical systems. Let's take a closer look at diodes and triodes, which are fundamental types of valves. A diode, essentially, is the simplest valve, with two main components, a cathode and an anode. Its primary function is to allow current to flow in one direction only, acting as a rectifier. This makes it crucial in converting alternating current to direct current. Now, moving on to triodes, these are a bit more complex. They have three elements, a cathode, an anode, and a control grid placed between them. The control grid is what differentiates triodes from diodes, as it allows us to control the flow of electrons from the cathode to the anode. This control capability means triodes can amplify signals, which was a major breakthrough in electronics. Connecting this to the overall theme, both diodes and triodes played pivotal roles in early electronic circuits. Diodes paved the way for efficient power rectification, while triodes opened up possibilities for amplification and signal processing. Understanding these valves helps us appreciate the evolution of electronic technology from simple components to complex systems. Let's take a look at the valves of the heart, or veins. In electronics, a thermionic valve is a device that allows current to flow in only one direction. This concept of unidirectional flow is actually quite similar to how blood flows through our heart and veins, ensuring it moves efficiently without backflow. The table on this slide helps clarify what a valve does. It's essentially a device that transmits flow in just one direction. Common examples of such valves include those found in our cardiovascular system, like the heart valves, which keep the blood moving forward, and in electronic circuits, where thermionic valves, or vacuum tubes, control the direction of electrical current. Understanding these valves, whether in biology or electronics, highlights how crucial unidirectional flow is for proper function and efficiency in both systems. There are various types of thermionic valves, and these are typically named based on the number of electrodes they contain. The most common types you'll encounter are the diode valve and the triode valve. A diode valve, as the name suggests, has just two electrodes, the cathode and the anode. It primarily functions as a rectifier, allowing current to flow in one direction only. On the other hand, the triode valve adds a third electrode called the grid, which gives us more control over the flow of electrons. This makes the triode much more versatile, especially for amplification purposes. Understanding the differences between these types is crucial because each plays a distinct role in electronic circuits, and they are foundational to how early electronics were developed. These distinctions also connect to the overall theme of how electronic signals are manipulated and controlled in various devices. This is the simplest form of thermionic valve, and it contains a cathode with a filament and an anode, all enclosed in a sealed glass tube. Now, the valve can either be evacuated, meaning all the air is removed, or it might contain a small amount of inert gas at low pressure to improve its operation. For current to flow through this valve, the filament needs to be heated up. When we do that, it emits electrons through a process called thermionic emission. Think of it as the filament giving off electrons when it gets hot enough. Once the electrons are emitted, applying a potential difference, or PD, makes the anode or plate positive relative to the cathode. This positive charge then attracts the electrons, allowing current to pass through the valve. And that's basically how a diode valve works, using heat to generate electrons and an electric field to control the flow of current. It's fundamental to understanding how these early electronic components operated in circuits. The electrons that are emitted from the cathode are attracted to the positive anode, creating an electrical current that flows across the device. Now, when we reverse the applied potential difference, or PD, so that the plate, which acts as the anode, becomes negative relative to the cathode, something interesting happens. In this reversed setup, no current flows through the device. This tells us that electrons can only pass from the cathode to the plate, not in the reverse direction. This unidirectional flow of electrons is a fundamental concept of diodes, often called valves, because they allow current to flow in only one direction. It's this property that makes diodes so useful in controlling electrical current in circuits, ensuring it flows only where we want it to. So, in essence, the diode acts as a one-way valve for electrical current, which is a key principle in many electronic devices. The intensity of the current flowing across the valve depends mainly on two factors: the heating of the filament and the potential difference, or PD, between the filament and the plate. When we apply more current to the filament, it heats up more, which causes it to emit a greater number of electrons. Now, this increase in emitted electrons means there are more particles available to carry the current. But it's not just about the number of electrons. The PD between the filament and the plate also plays a crucial role. If we increase this potential difference, we're effectively creating a stronger force to attract those electrons toward the plate. So, by increasing both the filament heating and the PD, we're essentially boosting the current flow through the valve. This interplay is fundamental in controlling how valves operate, especially in amplifiers. And as you can see, this is closely related to the diode valve concept, where controlling electron flow is key to their function. Let's take a moment to look at diodes and valves, which are fundamental components in electronics. A diode, as many of you know, essentially acts as a one-way street for electrical current. It allows current to flow in one direction, but blocks it in the opposite direction. This simple yet powerful function is crucial in converting AC to DC, among other applications. Now, valves, also known as vacuum tubes, serve a similar purpose but work on different principles. They use a vacuum and controlled electron flow to amplify signals or switch currents. While valves are largely replaced by solid-state devices like diodes today, understanding them helps us see the evolution of electronic components. Both diodes and valves are essential in controlling electrical flow, which ties into our broader theme of how different components manage and manipulate signals in electronic systems. Recognizing their functions helps us appreciate the progression from early vacuum tubes to modern semiconductor devices. Today, I'll be talking about the triode valve, which is a fundamental electronic device. Essentially, it contains three main electrodes: the cathode, the grid, and the anode. The cathode is where the electrons originate, and the anode is where they are collected. The grid, which is placed between these two, plays a crucial role in controlling the flow of electrons. Its potential can be altered, which means we can regulate the current passing through the valve. The grid surrounds the filament, and it can be designed in different ways. One common design is a metal cylinder that's perforated, allowing electrons to pass through while still controlling their flow. Alternatively, it may be a spiral of metal wire, which also serves to control the electron movement. This control capability is what makes the triode so important in amplification and switching applications. It's a key component in early electronic circuits, and understanding its structure helps us grasp how the basic principles of electronics evolved. So, in essence, the triode acts as a gatekeeper, modulating the flow of electrons between the cathode and anode through the grid. When we heat the filament, much like in a diode, current flows in only one direction, from the plate to the cathode. Now, if the grid is uncharged, it doesn't really influence this current flow at all. But if we apply a negative charge to the grid from an external source, it acts like a repellent for the electrons. This repulsion can reduce the current flow significantly or even stop it entirely. Conversely, if we give the grid a positive charge, it attracts the electrons, allowing the current to pass through freely. This is the basic principle behind a triode valve, where the grid controls the flow of current, making it a fundamental component in amplification and switching applications. All of these points show how the grid's voltage directly influences the current, which is central to understanding how these valves work within larger electronic systems. Let's take a moment to look at the triode valve. The triode is a fundamental electronic component that played a crucial role in early electronics. Essentially, it's a type of vacuum tube that controls electrical current using three elements: the cathode, the anode, and a control grid. The control grid is what makes it so effective for amplification purposes. By applying a small voltage to the grid, we can regulate a much larger current flowing between the cathode and anode. This ability to amplify signals was revolutionary and paved the way for the development of many modern electronic devices. Understanding the triode valve helps us see how early electronics transitioned from simple circuits to more complex and powerful systems. It's a key piece of the puzzle in the evolution of electronic technology. Semiconductors are truly the backbone of modern technology. They are essential components in almost all electronic devices we rely on today. What makes semiconductors so fascinating is their unique ability to act as both conductors and insulators, depending on the conditions. This dual nature allows us to control electrical signals very precisely. Think of semiconductors as the fundamental building blocks for chips, transistors, and integrated circuits. These tiny components enable the processing power of computers, smartphones, and even the latest AI technologies. As the world becomes more digital and connected, the importance of semiconductors only grows. Connecting this to our overall theme, semiconductors highlight how innovation in materials science directly impacts technological advancement. They are a perfect example of how understanding and manipulating material properties can transform entire industries. So, as we look ahead, the evolution of semiconductors will continue to drive progress across all sectors of the economy. Semiconductors are usually metals, which means they have some unique characteristics compared to insulators and conductors. Due to thermal agitation or the addition of impurities, these materials develop electrons that are free to conduct current. This free movement of electrons is what allows semiconductors to control electrical flow, making them essential in modern electronics. Now, a key point to remember is that semiconductors can be classified as either N-type or P-type. This classification depends on the type of impurities added and how they alter the material's electrical properties. Understanding these two types is fundamental because they form the basis of how diodes, transistors, and many other electronic components function. So, in essence, the ability to manipulate and control the conductivity of semiconductors through doping is what makes them so versatile and vital in the tech world. In an N-type semiconductor, we have an excess of electrons, which are the primary carriers of current. These free electrons move easily and conduct electricity efficiently. On the other hand, in a P-type semiconductor, there's a deficiency of electrons, which creates positive holes. These holes act as positive charge carriers, allowing current to flow as electrons jump into these holes. Now, when we fuse an N-type and a P-type semiconductor together, something interesting happens. Electrons from the N side can only pass into the P side in one direction. Specifically from N to P, this unidirectional flow effectively makes the junction act like a valve or a one-way switch for current. It's this property that forms the basis for many semiconductor devices, like diodes, which are essential components in circuits. So, understanding this directional flow and the creation of positive holes helps us grasp how semiconductors control and direct current in electronic devices. Let's take a closer look at silicon, which is a fundamental material in electronics. An atom of silicon has an atomic number of 14, meaning it has 14 protons and, in a neutral state, 14 electrons. Out of these, 4 electrons are in its outermost shell, or valence shell. In a crystal of silicon, these valence electrons are involved in forming bonds with neighboring silicon atoms, creating a stable, structured network. Because all the electrons are engaged in bonding, there are no free electrons available to carry an electric current. This is what makes pure silicon a poor conductor. It's essentially an insulator in this pure form. But here, where things get interesting. When we introduce certain other materials, like phosphorus, into silicon, this process is called doping. We change its electrical properties. Phosphorus has an atomic number of 15, with 5 electrons in its outer shell. When added to silicon, the extra electron from phosphorus doesn't get involved in bonding, but becomes a free electron within the silicon crystal. This creates what's called an N-type silicon, or N-type semiconductor. The N stands for negative, referring to the negative charge of the free electrons that can now move around and conduct electricity. This modification transforms silicon from an insulator to a conductor under certain conditions, which is crucial for creating electronic components like diodes and transistors. So, in summary, pure silicon with no free electrons acts as an insulator, but by doping it with elements like phosphorus, we create N-type semiconductors that can transmit electric current, an essential principle in modern electronics. When silicon and phosphorus form covalent bonds, what happens is that 4 electrons from phosphorus each make a bond with 4 electrons from silicon. This creates a stable structure, but importantly, 1 electron from the phosphorus atom is left unpaired. This unpaired electron is free to move around because it's not held in a bond with any other atom. And this is crucial because these free electrons can carry current, especially when the material is connected to a power source, similar to how conductors work. This type of material, where extra electrons are available to conduct electricity, is called an N-type semiconductor. The N stands for negative, highlighting that the charge carriers are negatively charged electrons. So, in the context of our overall discussion on semiconductors, understanding how these free electrons behave in N-type materials helps us grasp how they can be used in electronic devices to control electrical current. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. So, when silicon is combined with certain other elements like aluminum, which has an atomic number of 13, interesting things happen. The key point here is that aluminum has 3 outer electrons, and these electrons can form bonds with silicon. Specifically, those 3 outer electrons of aluminum bond with 3 electrons in the outer orbit of silicon. This bonding process creates a stable structure. However, there's a twist when it comes to the 4th electron of silicon. Since aluminum doesn't have an available electron to bond with that 4th electron of silicon, this leaves a missing electron in the structure. We call this missing electron a hole, and it acts like a positive charge carrier in the material. This process is fundamental to creating what's known as a p-type semiconductor. Essentially, by introducing aluminum into silicon, we're creating an environment where holes become the primary charge carriers, which is essential for the behavior of p-type semiconductors. Understanding this bonding and the creation of holes helps us see how doping modifies the electrical properties of silicon, enabling us to control how current flows through these materials in electronic devices. When a p-type semiconductor is created, a process called doping introduces impurities that affect how electrons move. When we apply a positive potential, or a positive voltage, to such a material, electrons start to move from some of the atoms into unoccupied bonds, or holes, that are closer to the positive pole. As these electrons leave the negative side and head toward the positive, the holes, which are basically missing electrons, appear to move from the positive side toward the negative. This movement of electrons and holes creates an electric current, which is the fundamental concept behind semiconductor operation. The interesting part here is that the material that allows this current to flow through the movement of these holes, instead of just electrons, is called a p-type semiconductor. So, in essence, a p-type semiconductor is a material where the majority charge carriers are holes, and these holes facilitate the flow of current when a voltage is applied. This concept is crucial because it helps us understand how different types of semiconductors work together in devices, forming the foundation for everything from diodes to transistors. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's wrap up with a quick overview of some key resources. First, we have Electrotherapy Simplified by Nanda, which offers a clear and straightforward explanation of electrotherapy principles. Then, Clayton's Electrotherapy provides practical insights into how this modality can be applied effectively in clinical settings. Finally, Sheila Kitchen's Electrotherapy Evidence-Based Practice emphasizes the importance of grounding our interventions in solid research. These references are essential for deepening our understanding and ensuring we're practicing in an evidence-based manner. Remember, integrating these resources helps us deliver safe, effective, and scientifically supported care.